We can take our seats. We can get started with the last session of the afternoon. Okay, welcome back. I'm Howard Schmidt. I'm glad to be here, Wade. Thank you. I'm the Executive Director of the Carbon Nanotechnology Laboratory here at Rice. I have the privilege of working with Dr. Hauge and Dr. Smalley. My next privilege is to introduce the speakers for the last session this afternoon, which is on solar thermal power sources. Our first speaker is Mr. Frank Wilkins, who runs the solar thermal program for the U.S. Department of Energy in Washington.
Hi. I am from the Department of Energy, and we've heard a lot about the Department of Energy this morning. Not all of it good, but bear with me. When Amy called me to ask about this seminar, she said, well, the purpose of it is to discuss policy. So I took a flyer and said, well, maybe I should discuss policy at DOE. So that's going to be the sort of the theme of what my discussion is going to be about. The other thing, though, is that unlike 95% of the rest of the speakers, I am not going to be talking about photovoltaics. I'm going to be talking about concentrating solar power, which is a thermal-based solar energy. But given that I'm from the Department of Energy, I'll also start off with a disclaimer in that I do not make policy at the Department of Energy. That is left to the political appointees. I am not a political appointee. All I can do is hope to influence policy, and I can only do that if allowed by my boss, who is a political appointee. So anyway, with having said that, that obviously doesn't work. What's the... That one. Okay, so what I want to do is describe the technology a little bit, talk about some of the policy changes that we have, and then get into some of the cost reductions and the strategy for getting that. Sorry, sir. Let me go ahead and wire me up. Okay. These are the technologies: parabolic troughs, parabolic dishes, power towers, and concentrating photovoltaics. I would be remiss if I didn't mention the fact that the power tower concept back in the 70s was partly developed by some folks just down the road at the University of Houston, and they've been a long-time partners of the Department of Energy. Now I have a short video that shows a little bit about three of those technologies. This is a system a parabolic trough system in Southern California. It's 80 megawatts. In the center of it is the steam turbine, which is the power block. This is a central receiver. This is also in Southern California. This was a 10 megawatt experiment with a set of heliostats or reflective mirrors that focus the energy on a central tower. And finally, this is a parabolic dish. This follows the sun during the course of the day, reflecting the sun's energy on a Stirling engine, which is located at the focal point. So those are three of the technologies. Generally speaking, these things are best suited for large projects. The power towers and the troughs in particular are best, where I say best, they're most economic when you're talking about 50, 100, 200 megawatt projects. Generally, they use curved mirrors to reflect the sun's energy to a point. That point gets very hot, produces steam, and then it goes to a sort of a conventional power block. One of the things that makes this thing a advantage, particularly to utilities, is that some of these technologies can store energy thermally. That means that you can have the sun's energy in the morning, perhaps when the utility doesn't need it so much. You store it, and then you dispatch it to the grid later in the evening when the utility needs it. In Southern California, sometimes the peak goes as late as 9 o'clock in the evening. I guess one of the negatives about the technology is that the towers and troughs in particular need water. just like a conventional coal-fired plant. Although you could go to dry cooling, which reduces the water requirements, but it gives you a penalty in cost. Okay, getting into the policy. This is a particularly good example of policy because right now this technology is sort of in a hole. And although you may think that things work slowly at DOE, I can say that policy can change in a nanosecond. And a great example of that would be when President Reagan became president. Under the presidency of Jimmy Carter, solar energy and renewables in general had a very high priority. Under the Reagan administrations, the priority was considerably lower. In this particular technology, at the end of the Carter administration, the annual budget was somewhere around $140 million. By the time the first senior Bush took office, the budget was closer to $20 million. So the policy changed very quickly and had a fairly dramatic impact. But that's not the only way that policy can change. And in this example, in the year 2000, the National Research Council recommended that DOE halt all R&D in CSP. And this came about because DOE asked the National Academy to review all of its renewable programs, and it did so. And the individual that was looking at CSP came back and said, well, there's three things wrong. One is it didn't have a sufficient industry to support the technology. Two was that any further R&D was not going to be able to drop the cost any, which I thought was a little bit odd for a National Academy type of conclusion. But the third was that they didn't feel that the technology could ever be deployed. Okay, based on that report, from the fiscal year 2002 through to the present, DOE has requested termination of the CSP program. Now, it may look like between 2000 and 2002 is a long time, but the way we do our budgeting, the 2002 budget request was the first opportunity that DOE had to impact the CSP request. Okay, but now it's also, you need to understand that DOE requests money. DOE doesn't make it. What we do is we put together a budget request, we send it off to Congress. Congress has its own gyrations on how it decides what to do, and then it signs a check and it'll send back what it thinks is appropriate. Well, in the case of CSP, it decided it was not going to follow DOE's lead, but it didn't ignore it either. During the decade of the 1990s, the CSP budget averaged around $20 million. For the last couple of years, it's been around $5 million, $5.5 million. So they have a sort of on life support, but they haven't decided to kill us. So we're sort of in a position where they're trying to figure out what to do next. Okay, now stepping back a second, back to 2001, Congress asked us to determine if it was feasible to build 1,000 megawatts of CSP new capacity in the Southwest. In 2002, we sent a report back that said, indeed, yes, it was feasible, although it would require some incentives for industry to go out and do that because the cost of solar technology is expensive and the cost of the power from it is more expensive than fossil fuels. Okay, so that evidently Congress liked, and I guess it helped keep them willing to fund the program to some degree. But we still had this NRC report hanging over our head. So what we did was we said, okay, let's get an independent engineering company, take a very detailed look at the technology and determine what they thought the cost reduction potential was going to be. So we asked this company called Sargent & Lundy to do that. And after several months, they generated a report that was about yay thick. They looked at every aspect of the technology. They talked to the labs. They talked to industry. And they came out and said, indeed, yes, you can reduce the cost of the technology fairly significantly if a variety of things were to happen. And I'll get to that in a little bit. Okay, well, this was fine, but I guess we at DOE said the only thing that can counteract an NRC study is another NRC study. So we went back to the NRC and said, would you take a look at this report and determine what you think about it? So at this point, we had the whole committee that was looking specifically at CSP, and they came out with some different answers than the first panel. And they said, yes, there is an industry that could support the technology, so that's not a problem. Yes, indeed, the R&D can reduce the cost, so that's not so much of a problem. But there was a sticking point. They said the cost of this technology is too expensive, and it's never going to be deployed. So that sort of left us hanging with 2 out of 3, but this ain't horseshoes, so we're still nowhere. So during the course of this last year, we've been developing a strategy to try to get over that hurdle of deployment. And we've heard through 5 or 6 different speakers today how the cost of technology comes down with deployment. Well, in CSP, there's been no deployment whatsoever, period, zip, for about 15 years. So we're trying to get over that hurdle. And here is sort of the bottom line of that independent engineering study that shows the cost of the technology versus deployment. Right now, we're at about 12, 14 cents a kilowatt hour. The Sargent Lundy report showed that you could get the cost down to around 4 cents a kilowatt hour if certain things were to happen. And on the right side of the picture, you can see how it breaks down. 42% of the cost reduction comes about by R&D. That we sort of have covered. 21% comes about by volume production. That's with industry building more and more of the reflectors and the receivers and what have you. And 37% of the cost comes down by building bigger systems. The system we showed in that little video with the troughs, the largest system there was 80 megawatts. And you can see from those first 3 bullets in blue at the top, when they built those trough systems back in the late 80s, early 90s, it started off with a 14 megawatt, and the largest was 80 megawatts, and you can see how that brought the cost down. So in the case now, we're looking at system size is going up to 200 megawatts. So that's how the cost can come down. And the National Academy said, hey, this looks reasonable, and they sort of went along with it. But again, they didn't agree with the fact that the systems could ever be deployed, and so therefore this curve didn't make a whole lot of difference. The other thing to notice on here, though, is that if you were to draw a vertical line at the 1,000 megawatt mark, you'd see that it intersects that green curve at around 7 cents a kilowatt hour. Now, that's not exactly where we need to be. Analysis shows that for intermediate power, you need to be somewhere in 5 to 6 cents a kilowatt hour. But we figure at 7 cents, we're close enough. And we've talked to a number of utilities over the last several months, and they agree that if you got down to 7 cents, they would become very interested in solar energy. So that, plus the fact that Congress has given us their interest in 1,000 megawatts, we decided to stick with it and develop a strategy based on 1,000 megawatts. Now, before I get into the deployment aspect of this strategy, given that this is a nanotech type of seminar, I threw in some things here that would be some opportunities that nanotechnology might be able to influence. Mostly we're sort of stuck in materials in that if we can raise the temperature of the systems, you increase the efficiency and you drop the cost. In most cases, the optics are such that we could increase the temperature of these operating systems quite a bit if we had the right materials. However, having said that, and what you see here is my original thoughts, but after having listened to some of the presentations this morning, I would say if you had to put your money somewhere in nanotechnology, put it in transmission. Transmission is a big problem in this country, so it's needed in its own sense. But we did a study on solar energy going out to 2050 about a year ago, and the limiting factor in CSP was transmission, primarily because for this technology to work, you need to be in an area where you don't get a lot of clouds, you have a very high direct solar insolation, and that's the Southwest. Okay, if you want to impact people that are living in Chicago, you need a way to get it from the Southwest up to the population centers. So if you could put together a low-cost transmission, that would be great for solar energy. Okay, I guess I'm not going to describe. This is the same curve you've seen 100 times for the PV folks. This is wind power, and it just shows that the more deployment, the lower the cost. So that's the same as we expect to happen with solar. Okay, what we do with a strategy? Well, to start off with, what's the resource? And you've seen some of these kinds of pictures before. The darker the color, the higher the solar insolation. We're very fortunate in the United States in that the Southwest has some of the best solar insolation in the world. But as it's been mentioned a couple times, it requires a lot of land. So we did some fairly detailed studies that said, okay, let's see how much land is available in the United States that would be appropriate. So we took the very best solar insolation areas and said, okay, let's filter out everything else. Let's filter out anything that has a slope greater than 1%, because that would make it easier to grade these things. Let's get rid of all the land that's used for anything like grazing, farmland, national parks, state parks, cities, roads, what have you. Get rid of all the stuff, all the land that's used for something productive, and what do you have left? And there you have here, it comes out to around 30,000 square miles. And this is just in 4 states. We picked 4 states to emphasize. That's California, Nevada, Arizona, and New Mexico. We picked those 4 states for 2 reasons. One, they have the best solar resources, and the second is that they all have a renewable portfolio standard, so there's a hint there that they're interested in renewable energy. Those 4 states right now are producing around 83,000 megawatts. Well, if you take those 30,000 square miles, and if you were to fill them up with solar, which we're not proposing to do, of course, but if you were, you would be able to generate over 4 million megawatts. So there's a lot of solar energy available. There's a lot of land available. So the solar resource is not a question, and the land availability is not a question. So what are the benefits? So we went to the states. We said, okay, here are the economic benefits, the environmental benefits, and the energy benefits. And I'll talk about each in time. And I'm starting off with the economic benefits because when we went to the states, generally we were talking to both the energy folks and the economic folks. And by and large, I'd have to say that it was the economic folks that were more interested in this than the energy folks. So what we did was we had the University of Nevada, Las Vegas do an economic study that said, if you were to build 1,000 megawatts in Nevada, what would the impact be? And these are some of the results. It said, during the construction of the thing, you would generate about 7,000 new jobs, both direct and indirect. After they were completed, it would sort of level out at around 2,000 jobs. So that's of interest to the states. The states were also interested in the fact that these plants would normally have to be built in some rural areas, and each of the states has some rural areas that needs to have an economic boost. So they like to have the flexibility of putting these places where it can do some good economically to some areas that they'd like to see grow a bit. The net impact to the gross state product would be on the order of $300 million a year. So given that all the states right now are sort of like the federal government in a bit of a financial bind, jobs and economic input to the state is something that they're interested in. The environmental benefits, these are actually all the rest of these things are pretty much would be the same for photovoltaics or any kind of renewable energy. A lot of pluses for air quality. Particularly in the Southwest, the states are worried about haze. And that relates again back to economics because they get a lot of tourists that go to the various state or national parks to see the grand vistas. And if the grand vistas are real hazy, they don't get as excited and they don't come back. So there's tourist money to be lost. In the way of energy, the states are worried about price volatility. There were some pictures here before about the spikes, particularly in California a year or so ago, were pretty draconian. They're worried about what's going to happen in any given time in the future. Solar energy, once you've got it, it's pretty flat. you know what it's going to cost for the next 20, 30 years. And they're also worried about some administration sometime in the future saying, hey, we got to do something about carbon, and imposing some kind of a price on carbon emissions. So these are the things that we've been pitching to the states, and some of the states trying to address some of the states' concerns. So these are the benefits. And what's the cost? Now, right now, each of those states have a renewable portfolio standard, but there's not a lot of solar going in. The reason being that the utilities in the states, and the way the renewable portfolio is generally worded, it goes for the lowest renewable option. So generally, these things generate wind projects. But we said, okay, if you were to modify the renewable portfolio standard to enable large-scale solar, what would the impact be to the ratepayer? And we were looking at this thing from the point of view that we were not going to ask the state to appropriate $1,900 million, and for certain, the federal government was not going to appropriate $1,900 million. So this was going to be somewhat revenue neutral for the state and federal government, putting the burden of this thing on the people. But anyway, the way it turns out is that if you built 500 megawatts in California, the average cost to the ratepayer would be 5 cents a month. 200 megawatts in New Mexico is 69 cents. The reason why there's that discrepancy is that there's just so many more people in California. So anyway, nobody wants to increase the rates to anybody, but if you want to develop the technology, this is one way you could do it. How this would ever be done, again, this is not the federal government telling the states they got to do anything. This is us trying to convince them it's in their best interest to do it. How they would do it, if they do it, is up to them. What's happening right now in those states, in June, Governors Schwarzenegger and Richardson included the 1,000 megawatt of CSP power in a bigger, what they call a clean energy initiative through the Western Governors Association. And that bigger initiative is 30,000 megawatts. So we're 1,000 out of the 30. And as a result of that, we have now a cooperative agreement with the Western Governors Association to help determine how to implement that 1,000 megawatts. After nothing being built since the very early 90s, Arizona is building a 1 megawatt Trough plant. Nevada, within a month or two, will start building a 50 megawatt Trough plant near Boulder City. New Mexico formed a task force to identify a large-scale CSP project that will be recommended to the governor sometime in January. Whether that's a 50 megawatt or a 100 megawatt is to be determined, but something's going to happen. And I guess California has formed a task force to develop a solar strategy for the state. And I guess we were out there talking to the Deputy Secretary of Energy a couple of weeks ago, and he indicated that CSP would be part of that solar strategy. So things are happening. Where this leads is another question, but things are happening. Summary, and this is some of the same things you've heard before 5 or 6 times now. Solar energy resource in the Southwest is huge and largely just sitting there untapped. Electricity generation is not only an environmental and energy boon, it is an economic advantage. But to get there, you need both R&D and deployment. And the strategy is for the Department of Energy to produce the R&D part of the equation and have the states do the deployment part of the thing. Again, getting back to the fact that this is all designed to change the policy on CSP, and whether it does that or not is open for conjecture. We're still in the process of going through this exercise. That's it.
Thank you very much for that talk. Our next speaker is Dr. Jacob Carney, who's the director of the Center for Energy Research at the Weizmann Institute of Technology in Israel. Dr. Carney.
Okay, here we go. Okay, this is the quality it's going to be now?
It's better from here than from...
Okay. I'm the last speaker here. I'm grateful for being here. The audience is smaller and I think probably a little bit saturated, so let me start with the conclusions. And don't expect me in the next 20 minutes to be able to back up all of them, but there are about 50 slides after that I can. Well, I think Gregor will disagree, but according to our analysis, solar energy is the only renewable energy available in large enough quantity to reduce, or at least to lessen, and that's the key right now, the increase in use of fossil fuels. Solar energy is supplemented in time with clean and safe and proliferation-proof nuclear technology can provide all of mankind needs for many years. We just have to do it. Large-scale economically competitive solar technology have been tested and can be commercially available in 5 to 10 years. And I'm not talking just about economy of scale here. These are things that can become competitive, cost-effective in relatively small quantities. And I'll be talking about that. And perhaps the key issue that a new research can lead to further development and improvement and widespread use of solar energy. We have been talking here about energy generation, electricity generation, but electricity generation only accounts for 30 to 40% of the entire energy consumption in a modern country. And so even if we solve part of that problem, we are not going to solve the entire problem. So we need new research, and I'll cover it, just some of it: cost-effective electricity generation, clean fuel production and material synthesis, more efficient, lower-cost solar cells, people have talked about that, various application of domestic needs, space cooling, weather heating, and so on, energy saving and improved conditions in urban planning, and medical application, even biomass gasification, so on and so on, much more. Okay, this is the problem in a nutshell. The problem is being presented here in much greater detail and more talent than I can do it. So let me just go to the there are a few things I want to say about this slide. The first thing to remember is that the people that made this analysis also predicted that the price of a barrel of oil will be between $20 and $30 in the next 20 years. Secondly, again, I want to emphasize that this is the total consumption, not just the power generation. And two other aspects that we have to bear in mind is first that the carbon emission grows at a faster rate than the generation. And the reason for it is because we are resorting to a less and less rich resources. What used to be unconventional fuel is now we're starting to use it. The technology to produce it is more expensive. So we are generating more carbon now than we did for the same megawatt of power, say, in the 1970s. So carbon emission, this is the same report can show that. Also, we're not talking about other pollutants. We're talking about if we will keep the NOx and the sulfur restriction as they are now, and we continue to increase the production, we're going to have a problem with NOx and sulfur. So we're going to have to reduce the ppm of NOx and sulfur as we go up with the production in order to keep the amount of them stable in the atmosphere, and also very difficult and very expensive to do it the way it is done now. So I want to give another look at this from other aspects. And I have to admit that I added this slide after having a conversation over dinner last night. The nuclear options. The present option is using uranium isotope 235. This was developed as a weapon. It is then was used, we decided also to use it as a power producing alternative. But people didn't pay attention when they were obviously the Manhattan Project, they didn't care about efficiency use. We can only use about 5% of the natural uranium in the world because only, 0.5%, this is a mistake, because only 0.7% of the uranium in the world is a 2.35 isotope. And perhaps the most important thing is if you don't solve this problem, it's going to be irresponsible to make this a large-scale and growing-scale technology all over the world. Totally irresponsible. These problems are solvable. They'll take time and they'll take money. The second alternative that I personally like is that the use of clean fission fuels, such as thorium, and work has been done on it in the 90s and still going on in CERN. These cannot be used as weapons. They're safe, and they have a very short half-life. The problem is they require about 20 or 30 years to develop, and some relatively large funds, much larger than what solar would take. The last option is still 30 years, more than 30 years from commercialization. And when I was very young, I was told in the 50s it was 30 years away for commercialization. So I believe that this is a viable option. The point is timing. We don't have 20 or 30 years to wait until we impose a solution. So what I recommend is to go with solar within the next 5 to 10 years, and from then replace the coal plants in times with clean nuclear. Here is a case study, China, and this is taken all from the China Daily of September 24th this year. I happened to be in China at the time, and I picked up the paper, and it was a large article. This is probably one of the most controlled newspapers in the world. And there was an interview with the former energy minister, and here is the data. Total capacity of China as of the end of 2002 is 385 gigawatt. Coal is 80% of it, so it's about 300 gigawatts. And the main thing is 24 out of 31 provinces in China have a problem with capacity. Shortage output. You imagine that 35 states in the United States would just, sometime between 4 and 8 p.m. will not have power. This is happening in China now. So says the Ministry of Energy, the former Minister of Energy, by 2010, we will need 1,500 gigawatts. That the capacity of the United States, what is it now, 800 gigawatts or something of that order? This is what China will need, an increase of 1,200, almost 1,200 gigawatts in the next 5 years. The total resources of hydraulic and wind are, as I said, it's written down here. So even in a very, very unlike possibility, even energy impossibility, they would use all the hydraulic and wind resources, they still will need 225 gigawatts by the year 2010. And obviously that can't happen. And then what are they going to do? They're not going to stop going in 2010, and this is not enough. Where is China going? Is China going coal and nuclear? And they are not going to be considering, they're not going to have scrubbers on the coal plants. Somebody out there says, I need power. They're going to put coal, and they have a lot of coal. So China by itself, and I'm not talking about India yet, which is the same size problem, is a world catastrophe, could be a world catastrophe as far as climate change. And the Chinese really want it. They really do, at least in the conference that I was at and the email that followed it from all different parts of China. They want to go clean coal. They're thinking about that. And they want to go solar, and they're thinking about clean and safe nuclear energy. But again, timing. Timing is the problem. Okay, that was all I wanted to say about that. Just briefly about what's happening in Israel. Israel is a small country, so it's a case study. Here is the growth of electricity in the last 30 years. And how does it match with the growth of population? Well, obviously you see that electricity demand grows much faster than the population growth. And that's what this is a classical case in that case, in this year. And I think this is the most important thing about this slide. The total energy consumption increased by a factor of 2.5, while the population growth was about 65%. And I think that's another part of the problem. We may come to a point in a country like China that there isn't a population growth, or Europe, but there's going to be still a high growth of demand of power. What kind of renewable energy resources Israel has? Well, this is all taken from the Ministry of Energy in Israel, so I'm sorry for all these funny names there, but Israel has a lot of solar power in the southern part of the country. And that's what we're going to develop. There is some wind, really not that much. The problem is that all this area is taken. It's not like the United States. You have vast areas that was presented by Frank here before. This is all divided, and this is real estate that you're going to have a problem with. And I'm going to take it from 2 points of view. As a solar energy person, I was driving on a highway down south somewhere here, and I measured the length of the adjacent fence to that highway that is part of the fence that surrounded the nuclear reactor that doesn't exist over there. And I assumed that was a square fence, and I figured out how much solar energy you could put in there, and that was about a half of the capacity of Israel. Right in that, and we all know that it goes farther deep into the desert than what's by the road. And on the other hand, when they want to put now 100 megawatts in the desert, they said they barely have enough room for that. They were talking about 100 megawatts of Trough in the desert. Barely have room for that because the army controls part of the desert and the Nature Society the other parts, and it's all taken. So it's an issue. Okay, government of Israel is trying to support renewable energy, basically by doing similar things to what the rest of the world is doing. They're giving incentive by subsidizing the price, about 1.5 to 2 cents per kilowatt hour. And they also have set up a guideline that they want the total renewable energy to be 5% of the total capacity by 2016. This is a much more modest goal than we have in California, for example. But since they know that it's going to be very difficult to meet it, so they created an interministerial team to propose concrete implementation steps. So meaning that they find another committee to discuss what the first committee said, and so on and so on. So nobody really is serious about that. Okay. Just say I'm not going to have to do a lot of that because Frank already covered most of that. so I'll just concentrate on Israel. In the oil crisis of the 70s, the Israeli government did something right. They created a policy to put roof collectors. There's a hot water roof collector, not solar thermal. Hot water roof collector on top of the buildings. It's part of the building codes in Israel. Most of the buildings have those. So most of us get hot water from solar energy, and the government tells me that that saves about 3% of the fuel imports, which is very nice. This is an established market. It's not rebated. It's not subsidized, and it works well. This was discussed at Trough plants. The only thing I have to say about this is, first of all, this technology was developed by an Israeli company now that went bankrupt around in 92, Luz, and the only place they could find to put this technology, it was too expensive, was in California because of some legislations. They still haven't been able to build a plant in Israel. This technology is now, development of this technology, improvement of the receivers, much better parts are being designed and built in Israel and in Europe. So these technologies keep on getting better, and the numbers I hear is that it's going to be about $3 a watt or $2.50 a watt at large scale, which is cheaper than PV and yet too expensive. These are the other concentrated solar technologies that Frank has discussed before. I just wanted to say a few words about this. Honestly, I don't understand why it wasn't discussed at all, but there is a new technology out there called concentrated photovoltaic. The idea is to replace cell area with the concentrated area, which are cheaper. These are three of the kind of different technology, different concentrated photovoltaics that are being developed. Some of it we are helping in. Okay, that's a fun part, and this is what we do in Israel. First of all, this is our solar laboratory, which is really a nice solar tower designed for a campus, designed for an academic campus. So you have 5 levels of different, where you could do tests in, and you can use different arrangement of the concentrators. We put up a tower reflector that beams down the light, so we can do some work down here, facing up all the time. This works very nicely when you do some chemistry work using solids. A great toy, great toy. Main reason I'm working there is this facility. Now, what have we been able to develop? I think that one of the things that has a great promise, and this is addressing the issue where we can be really cost effective, is a solarized gas turbine. It's not only a dish technology as shown here, it can also be a tower technology as being developed in other parts of the world, mostly by DLR in Germany. This technology is nice. What you're essentially going to do, and we can see it in this slide, you take a gas turbine, which is shown here, and you integrate it with a solar receiver. And the idea is the receiver replaces the combustor. So all you do is use solar energy to heat up air. When you don't have solar energy or it's not sufficient, you can always tap it with fuel. The hybridization is totally integrated. It's in the system. You can add storage anytime, but you don't have to have storage. You can provide power in the evening hours using fuels. So essentially, we're working in cooperation with several companies. One of them is Breton Energy that built this turbine. The receiver technology was developed at the Weizmann Institute and is now further developed with an Israeli company. So basically, this shows some of the tests that we've done. This is the first unit, 40 kilowatt thermal unit. And this is a 250 kilowatt thermal unit hooked with a Honeywell microturbine. doing tests. We use the Honeywell microturbine because we figure Honeywell is a solid company. They're not going to go away like the Capstones. And of course, Honeywell no longer is doing microturbines. Murphy is there. And as I said, the receiver really absorbed the concentrated sunlight and replacing the combustor. The neat thing here is that you really have a very high potential for high efficiency. The systems that I showed before can reach system efficiency, not power conversion efficiency, of nearly 40%. And this is what you're looking for in solar. And high efficiency means lower cost. Okay, I wanted to put this slide here showing what kind of dish concentrator there are out there. A lot of people put time into dish concentrator. These are 6 different, this is not a dish, but the trackers that you use can be used for a dish. And these are not the only dishes that are being used. There are many dishes in the world. You've got to pick up the best options or combine the good things from all of them and make it commercially or economically feasible, because the cost of the dish is going to drive the cost of the system. Okay, anybody in the solar field loves to do levelized energy costs, and everybody lies all the time. So, because you can make any assumption that you want, and I'm not going to go into it now. It's quite disgusting when you go to those meetings. So we went and got somebody else to do it, and I think Dan Resler can be trusted. He just created a model, and we had another model created that was done by an investor-owned utility. We had nothing to do with it, and basically the models, the results are pretty consistent. These are the dirty technology. These are state-of-the-art development, meaning that they work on really natural gas technologies. And these are the solars. Obviously, this does not take into account future developments and the lower cost, but pretty much what can be done right now or in larger scale. And this is fairly consistent with the number that was said before. I have to say that we use a number that are now very low, like $4 per million BTU. This is a very low number for what the cost of gas is now. That favors the non-solar technology, but the technology that we have here is still competitive. This is without any subsidies or anything. You can do solar, and this is a 10 megawatt. You can reach this value, between 10 and 50 megawatts. You could do solar that will be cost effective. New research that we are doing now, this is a test. This is a picture taken during those tests. We have a receiver here that uses carbon particles to heat the gas. The incredible result is that we will get in the same temperature, really about 2,000 degrees K, this receiver using air and using nitrogen, carbon dioxide, and argon. Now think about it. The carbon should have burned in the air. It didn't. We didn't believe the result. We repeated them several times until we melted the thermocouples. The thermocouple is platinum. Melting temperature of platinum, I think, is 2,100 or so. There's something going on here. The key is that this is very highly concentrated light. It's 5,000 suns. We can go to higher. So we're trying to figure out what happens there and why the carbon does not burn. Actually, it simply heats up the air faster than the kinetics of the chemistry. Not quite understood. This receiver has a very, many possibilities of being used for chemical reactions at very high temperatures. And this is what we're doing now with that. A key use of solar energy is going to be long-term storage, and the kind that will enable you to use solar energy away from the plant. The only way to do it is store it as fuel. And this is the basic concept. The basic concept is take some kind of reactant, add energy to it, solar energy, and comes up with something that has high energy value in it. Now then think about the application. Let's assume that just the reactant is water, and we have hydrogen and oxygen. Then you can drive it right here. Engine, fuel cell is an engine. Many people forget it, but fuel cell is not a storage device. It's an engine. You put fuel into it, out comes work. This is an engine, as far as I understand thermodynamics. So that engine could be an internal combustion engine, it could be a fuel cell, or anything else. But the basic idea is energy comes here from solar, and the solar fuel can be used somewhere else. It may not necessarily be as hydrogen. Some things that we can do along that line. One of the things is the Matam Reforming. Over 90% of the world hydrogen now is made with reforming, not just metal, but hydrocarbons reforming. You could use the syngas that you get here can be used to make methanol, ethanol. Another option here is, well, you can always burn it and get 30% more power. This reaction can go both ways. You can make syngas and methanate it, meaning taking the reaction back to the left and get the energy out and drive a Rankine cycle. You could do that. The problem is the transportation of the hydrogen, which is difficult. If it is solved, then this technology can be very nice. You actually don't use the methane because you recirculate the whole thing. The idea came with a nuclear reactor in Germany, was known as the Adam and Eve project in the 60s. Some people may remember it. This is an idea of how to dissociate water. Now, we try, first of all, obviously, we do electrolysis is a well-known process. Not very economical, but people use it. We tried and succeeded in splitting water at 3,000 degrees K, but obviously only about 6 or 7 molecules you eventually splitted, and you use all your power on the thermal issues, and this is not a practical solution. Actually, the reason for doing it started from a seminar at the University of Minnesota where Professor Ed Fletcher, one of my teachers, said there that he could do that, and Yves Sparrow said, no, you can't. So Fletcher went and did it, and again, but it's not an economic process. The idea is to try to do it somewhere in between, meaning do electrolysis at high temperature, so you lower the free energy, and you lower the free energy. The total energy is the same. The free energy is lower because free energy is 0 when you get thermal equilibrium, when it's with thermal equilibrium. The nice thing, it fits very well with solar. Why? Because in solar, if you take here, you split the spectrum right here. You take some of the light to the photovoltaic, the waveband that the photovoltaics wants to use, and the rest you use for thermal energy. Then you can do both. You can have the thermal energy and solar, and the idea is just to do a system balance here, system energy balance, and you can have a very nice, highly efficient, high-temperature electrolysis. Now, this is a project we just started in cooperation with UMass and the University of Alabama and some other nice people. And perhaps this is the main thing that I hope I think it's probably the most difficult process, but also with the greatest potential. Zinc here is a case study. Zinc is easy. But if you take a metal oxide and split it, here you can split, obviously it's easier to do it like that. But let's split the metal oxide. This is fuel. It's got a value as a metal, but it can also be used as a fuel because you can always dip the zinc in water and get zinc oxide and hydrogen. The nice feature of this is the zinc or another metal can be transported and stored much better, it's much easier to do than hydrogen. And the reverse reaction, the zinc-water reaction, you do in the car. Now, this is better than using hydrates because you also get thermal energy in addition to hydrogen in the car. Now, zinc is what we are doing right now. It's the first level because it's relatively easy and well known, but zinc is too heavy, and the trick is to find other material that will be lighter. And there are, and we're starting to work on that, but this is the place where the material experts are. If we can find a light enough material that has high energy content, that you can start with an oxide or some raw material and work backward, that could be a technology that will eliminate or at least alleviate many of the storage and transportation and general handling problem with hydrogen, still be a part of the hydrogen economy. This is a picture of that reactor and the process that we are doing there. And back to the conclusions. So, but in the spirit of being controversial, and I'm the last speaker, and for those of you who are still awake, I wasn't going to show this slide, but after hearing some talk about 9/11 being in a public perception more important than changes of the climate and energy problem, I've got to go back and show this one. Now, take another look at it. This is very controversial, and I agree, and you don't have to agree with me, but I think that 9/11 is an aberration, just like maybe the Cold War is an aberration. But the energy crisis and the climate change is part of the development of our species. And if we don't solve that problem, our culture is going to go away. It's just how it is. And it may happen sooner than we thought it would be in light of the demand of power in China and India. Unlike the energy crisis in the 70s that was politically motivated, the energy crisis now is due to a real shortage in economies that are growing faster than what we can supply. Okay. So this is a good point to start the discussion.
Thank you very much, Dr. Carney. Now we have about 15 minutes for questions and discussion. Rick.
I have a question for Frank Wilkins. For these solar troughs, you said that there's a need for water. I suppose it's cooling in the cycle. So if we went and actually covered 100 square miles of desert or more in solar troughs, how much water would we need?
Right. I don't know the specifics on that. It's again, it's the same as the coal plant.
That could be a showstopper in Nevada, couldn't it?
It's certainly something you'd have to think about, and I guess probably going to dry cooling would be an answer.
Then my follow-up question is, what is the increase in cost for dry cooling?
Right. I think it's on the order of $0.01 per kilowatt hour.
Really?
Prashant Kamath from Notre Dame. I just trying to get these thermal power figures. If you have to generate X amount or X megawatt of power, how do you weigh in thermal versus photovoltaic? Is there some kind of a threshold below which one is better than the other?
Well, my program develops both photovoltaics and thermals, so we're into making a portfolio. The advantage of photovoltaics is it's ubiquitous in that you can use it for anywhere from Maine to California. With solar thermal, you're pretty much stuck with the Southwest or the western part of the country. It's going to come down to economics. When we talk to the utilities, which is really only what CSP can go for, the utilities scale, large central projects, it comes down to one factor, and that's cost. They'll buy the lowest cost option that they have. And if PV is cheaper than CSP, they'll buy PV. If CSP is the cheaper option, they'll do that. Otherwise, they'll go for wind or whatever they can get cheap.
Yeah, there's a question back there.
This is Mike Hanratty with University of Texas. And I had a question about solar thermal as an application for generating heated water linked to adsorption chilling as a source of air conditioning. Have you seen, have you tested those types of applications? Do you see a lot of demand for that?
The Israeli company that is that actually now owns the technology of flues, named Soler, is concentrating into that. There is I have some slide that also shows some very neat ways to use solar thermal for cooling applications. There are two ways to do it. One, you have to do it on a small scale, really. It's something that may not fit Trough so well, and use some other type of concentrators that you can put on the top of your roof and use it as a domestic application. But it's been done.
Yes, sir.
I have just a suggestion and a question. The suggestion, you asked for another fuel. You may be aware of some work where sodium borohydride in water is used as basically a hydrogen storage medium, and the recycling is the problem because you make borate. And so the thought is that boron's pretty light, and maybe if you could solar thermally recycle the borate in water to make sodium borohydride, that would provide a nice cycle for the hydrogen carrier. So that's just a suggestion on a light element to think about recycling, which you may have already done. My question is, on the solar thermal systems, the concentrators need to do tracking, of course, right, to track the sun. And so one's always concerned about having moving mechanical parts over long times and large areas because lots of them, at least that's the word on the street, is that could be a problem. What's the experience in terms of actual operational time and costs that are associated with? Are these so reliable that they could be out there for 30 years and you'd never have to oil and lubricate them? And if not, what actually is the cost of actually operating costs of these trackers?
The systems I showed in Southern California at Luz, they've been operating since the late 1990s, 1980s, early 90s. So they've got about 15 years of operating experience. The company that actually there's I guess several companies that operate those systems have found that they operate better now than they did when they were first built, largely because they've gotten smarter at how to keep them operating. So, and how much does it cost? It's probably a couple cents a kilowatt hour.
Is that included in your cost, or that operational cost? So that was a fully amortized, including operational cost, and including downtime for fixing them and all that.
Exactly.
Thank you.
This question here.
What is the efficiency of the system? What fraction of the energy do you convert into electricity?
Well, it depends on which technology. The most efficient technology I showed up there was the parabolic dish. The one that we had, it topped out at around 30% net from solar to electricity. Although I guess Dr.
We've been able to reach about 35, and 40 is certainly feasible as we learn how to use them.
The trough is probably 13 or 14%. I guess, though, we tend not to look so much at efficiency as we would look at cost.
But that means the trough is very competitive, about the same as PV, right? 13, 14?
Mm-hmm. In terms of efficiency, it's in it.
Yeah. Thank you.
Yes.
By the way, excuse me, I'll take it back. It's 13% efficiency as annual average, not as peak efficiency. That's the difference. With PV, it's peak efficiency. So Trough is more efficient.
Regarding the combination of CSP and photovoltaics, Dr. Carney mentioned, I know that DOE also has a program. What do the economics look like for that system in terms of cents per kilowatt hour?
For the concentrating photovoltaic?
Yeah.
I don't know that we got that far. We were just starting to work on that with budget cuts. That was one of the things that we gave up on before we did a real thorough systems analysis. Our philosophy has always been that it's the PV program. That's Larry Krasmersky and Ken and those folks do the PV. They're developing some very high efficiency systems that operate under high concentrations. So essentially our goal was to take their stuff and put them in a dish, or in that case I showed a picture of a Fresnel lens. But we hadn't gotten to the point of coming out with that kind of a number.
The American company that we've been working with did some, Arizona Public Service, did some analysis there, and basically depends on the cost of the PV, of the triple junction cells PV. If I remember correctly, if the cell cost is $0.50 a watt, the system cost will be roughly $3 a watt, maybe $2.8 a watt. That's where they think it will more or less level.
There's two advantages, as you know. One is the thermodynamic efficiency will be higher, and then you replace the expensive cell with a lower cost PV. What's the relative contributions to the improvement for those two pieces?
They're conjugated, so it's hard to say. As the efficiency goes up, you need less collection area. So it's difficult for me to say. The cost of I can't say from the top of my head. But the bottom line, it seems to me like it would be about $1 a watt cheaper than the cheapest PV, flat PV that at least we have been able to analyze. There is also another very important issue that we did not mention today, and that is the rating of a solar power station is not the key. It's how much energy it produces a year. You can have two solar systems using different technologies that are rated at 100 megawatt, and one would produce twice as much energy every year than the other because it is optically better. It follows the sun better. It can use maybe some part of the diffuse energy or so on. As an example, if you take a simple photovoltaic system, flat silicon photovoltaic system, and you run it on a single axis like a Trough, tracking the sun, in a very crude way, you will be able to increase the amount of power that plant produces every year by 15–20%. So maybe the cost is worthwhile, and so on. That's part of the reason why we decided to go to a dish, because the dish is the best, uses the last drop of sun power every evening, or the first one in the morning too.
Did I hear you say that the dish is part of a big cost factor in this type of technology?
In any solar technology, the collection area is the cost driver.
And
so you have to be very efficient. The economic here are asking all the time about the efficiency because it's a cost driver. Am I right?
And so is there going to be improvements in that area in terms of cost, et cetera?
Efficiency is the key. Yeah. So if you get to obviously if you get if you get to a technology that is, say, it's 40% more efficient, 40% efficient relative to technology that is 13% efficient, you could afford more expensive power. The solar cells can be more expensive. You can really spoil the solar cells. You can use triple junctions. You can think solar cells are more expensive because the efficiency is high and you don't use that many cells. You use only a factor of 500, if that's the concentration ratio, for example.
Do you have any other questions? Yes, Wade.
A lot of the photovoltaic farms would be housed or placed in a desert area, and those same areas would often have a lot of wind blowing at times, and wind blows sand around, and sand can do damage to surfaces. And I'm curious about how robust these systems, either the lenses or reflectors of solar thermal or photovoltaic systems, are going to be to that kind of an environment. I mean, the best place to collect the energy is in a place that is not very nice to our packaging or optical units. So is that being factored in? Is that really an issue? And how do you clean these things and how do you protect them?
That is an area that's gotten a lot of research. One of the pictures that Dr. Carney put up there showed essentially a truck going down, washing the reflectors.
That's what made me think of it, yeah.
And indeed, laboratories like NREL and Sandia have developed hard surfaces on the front side of glass to minimize the sticking ability of the dust on the glass itself, so it's easier to wash them. Thus far, the experience with particularly the loose systems in Southern California, there's been a little bit of degradation, but it hasn't been significant.
It's really climate driven, but there've been a lot of research there. If you can develop a material that repels particles, and it's been done.
Yeah, sure.
That could be very helpful here.
But it
or
sounds
cleaning
like,
agents.
It sounds like it's not such a big problem, but
Look, where our solar tower is located, we have to clean every 3 months, like heavily, because we got a lot of humidity and sand. In Sandia, they never clean. In Tempe, they don't clean. They don't have to.
A question here?
I was speaking to the people at Tucson Electric Power, and they have a lot of wind, and they say that's a good thing because it cools the solar cells. So actually, it helps.
Yes, Rich.
Maybe you could imagine coatings that'll keep dust from forming, but sandblasting is another challenge. Has anyone looked at the great deserts around and seen how many of them would just be out of the question because of sandstorms? Does anybody know?
Wasn't there a system put into Saudi Arabia about 20 years ago? Was that Solaris, it's called? Is anybody familiar with that? I don't know if Larry's I heard that there was no real damage from sand over that 20-year period in Saudi Arabia. I think that so far I haven't heard major problems with sand as an issue, but
in fact, the reason this came up in my mind is I recently was in Bahrain, and on the way flying back, we flew over Saudi Arabia, and most of the time you couldn't see the ground because of the sand. I was wondering, here's this great resource, but the sand is a little bit of a problem.
Actually, I think the effect was that it cut back on the solar resource. That was the real effect.
Flat panel TVs don't obviously have the same problems that concentrators have. But when you have a concentrator, like we saw in the pictures, you're talking about a large farm. Out of the 7,000 employees that are needed to install it, I think I saw that 2,000 stay there, or there's 2,000 jobs created. And these jobs are cleaning the trough, oiling the moving parts. So definitely on a big scale array like that, you'll have to have maintenance, and maintenance is there. Obviously, you cannot afford that on a 4-kilowatt system on somebody's roof. So there is a difference in perception. Definitely some of these desert-mounted flat panels, they lose 3, 4, 5%, and then that's it. It stabilizes because they're typically at an angle of 40, 45 degrees. Sand accumulates and then just drops off. There'll be some periods where, indeed, if you have a sandstorm, the energy is going to be reduced. But cleaning is part of the game in a fairly large installation and is included in the equation.
I actually think agree it's going to be a huge problem because in airbase design, for example, where you have an example of an 1,100 person airbase deployed out into the field, there's pictures of these military tents out there, nice brown tents, but they're actually green tents because they've just been coated with the dust and the dirt, and so the sand just gets in everything and sticks on it. So, I mean, it's something that we've not looked at, and I think it's going to be a huge problem especially for military applications, but for other applications as well.
Amy?
Let me just add, when you're talking about the desert, I mean, we all picture different kinds of deserts. So what you have in Arizona is not the same as what's in the Sahara or Saudi Arabia. I mean, in places like that, you can have dune swells that shift by, just thousands of feet. So that's not going to be an area where solar is going to be possible. So I think you really have to define, we're not talking about putting these down in a sand somewhere in the Middle East where the sand moves around, in significant fashions.
Yeah, we'll have to glue the sand down with nanotechnology.
Right.
One last number, I've been quoted from Tucson Electric. They had budgeted 0.4 cents per kilowatt hour for maintenance, and their historical experience to date is 0.2 cents per kilowatt hour for maintenance in their solar farm.
Those are non-tracking.
Non-tracking, yeah. I'm in favor of non-tracking, actually.
We have no more questions or comments. We'll conclude for the day. Wade, do you want to have any wrap-up comments?
I think our brains are pretty fried to do any wrap-up, but just wanted to let you know that the first two speakers tomorrow, Larry Kazmierski and Nate Lewis, are going to switch spots. That's due to computer issues. I'll also remind you that we tried to send the word out, but lots of people didn't get it, that the official dress code of the conference is business casual, and it has been observed that ties can cut the blood supply to the brain and cause fuzzy thinking. So I recommend that you think about ties optional. And for those of you who are going to dinner, it's at 7:30 tonight, but I don't know the bus schedule. Wait a minute.
The bus will be leaving the hotel at 7:15.
Okay.
And there'll be a bus out front here now that'll take those people staying at the Warwick back if they need a ride back.
Great. See you at 8 o'clock sharp in the morning, and we'll continue.